Hi, so the today's class is the basic electronics engineering course code is EC201, EC101. Myself, Dr. Vishwarup Niyogi, Associate Professor and Head of the Department of EC JS College of Engineering. And things is that in the previous class we have already studied about something diode and some several equations and all those things. I can understand that you are confused about these things also. I know that I feel that about these things, but the matter is that today I want to give you some relief on that things that what are the things and what are the practical implications of this, and although all this matter we can representing today. The main things is that in case of the diode in the PN junctions diode, we can represent the diode is uh, if I'm introducing the you can introducing the DC in the diode. So in the forward bias that diode is working properly. Okay, so these things analysis we have to need to know, and in the reverse bias what actually happened, that things also we have to know. These two matters we have to discuss today. So as per the prerequisite, we have to know uh, that DC direct current, and also the AC signal, also the KVL, KCL, Kirchhoff law, Ohm's law, and all those things, the particular different kinds of circuit and Ohm's law, Kirchhoff's law, and KVL, KCL. These things are very much essential for you to understand. For today's class specifically, you have to know all these things. Otherwise, you cannot overcome these things. Okay, so this is very important for you. So next we go for the course outcome, that is the CO1, that is the study of the PN junctions diode, ideal diode model and its circuit analysis applications, and the diode of specific diodes. Learn how operational amplifiers are modeled and analyzed, and to design op-amp circuit to perform operations such as integrations, differentiation on electronic signal. Study the concept of the both positive and negative feedback in electronic circuit. Develop the capability to analyze and design the stability sample circuit containing non-linear element such as transistor, using concept of load lines, operating points, and incremental analysis. So specifically we are at present now stick to the diode, and for this is the COPO mapping of the subject. COPO mapping is there, and this is the CO and PO mapping of this subject. And things is that this is the module 2, that is a PN junctions diode applications and PN junctions formations and depletions region, a energy band diagram of the PN junctions at equilibrium and barrier energy, built-in potential at PN junctions, energy band diagram, and current through PN junctions at forward and reverse bias, VI characteristics and current expressions of the diode temperature, depletions, and VI characteristics of the diode, PN junctions breakdown and conditions, and avalanche and Zener breakdown concept of the junctions capacitance, and the Zener diode characteristics, diode half wave and full wave rectifier circuit and operations, IDC, RMS, VDC, RMS, VRMS, ripple factor without filter, efficiency of PIV, TUF, reductions of AC ripple using filtered circuit, quantitative analysis, design of the diode clipper and clamper circuit, extent, explanations with the example of applications of the Zener diode in regular circuit numericals problems are there. Okay, so these are all the things which we want to cover in this particular module, but in particularly today's topic is related to the PN junctions diode forward bias, reverse bias, and Zener diode. So we have to know about the practical circuitry analysis of the forward bias and reverse bias, and then the Zener diode. So there is, we just representing some symbolic representations of different kinds of diode. We have to know about all this. That is the conventional silicon diode. Conventional silicon diode. That is the Zener diode. That is Zener diode representations. That is Schottky diode. That is Schottky diode. That is light emitting diode, which is basically nothing but a LED. This is actually the LED which we are used specifically. So these are the different kind. Not only this, apart from that, there is several types of other diode is there. That is gun diode and other diode is there. But generally, specifically for you to know about the diode, these are the diode is very important for you. Next, I go for the specific representations of the forward bias of PN junctions. And in case of this forward bias, there is, you show the diode is there, and there is, you just representing the P, that is the forward bias, and there is a negative, that is the reverse bias conditions. There is the PN junctions, and in this PN junctions we are introducing the forward bias P, that is positive terminal of the diode, positive terminal of the battery to the anode, and negative terminal of the battery in the cathode. Okay, so in the reverse case, we just do it reverse. The negative terminal we are introducing in the anode, and positive terminal we are introducing in the cathode. Okay, so what happened, which we have already know about the previous case, that holes and electrons are combine each other and passing through away, and a huge current flow, and through that, uh, this is the graph. This is the graph which is representing like that a forward bias voltage. This is that we are applying the at present now DC current, DC voltage in the diode terminal, diode. Okay, and in the reverse time, in the reverse times, a very small amount of current is flowing. You show I am increasing the voltage, but there is no changing in the current. You show there is no changing in the current, very small changing in the current. Here, this is the current, this side is the current, this side is the current, and this side is the voltage. This side is the current, and this side is the voltage. Very small amount of changing the voltage. After that, a huge change in here, huge change in here. Why huge change? Because in the reverse bias conditions, the bond will break and huge current flow. So I am come to the matter. Before I am just representing again, it is, you show there is a forward bias conditions. You show this is the forward bias condition. So for that reason, the graph is looks like that. And it is the reverse bias conditions, the graph is looks like that. You show this is a huge length of this, because after a huge time bound it will happen. Now as per the avalanche said, in the PN junction there is a PN junctions is there, and after a voltage, after a certain voltage, all the bond will break and a huge current flow. That is actually explained, elaborated by the avalanche. Okay, so this is called the avalanche breakdown concept. Now and this is called the avalanche breakdown concept. But the avalanche cannot able to reach particular voltage. Avalanche cannot reach. They hypothetically, avalanche said that it will possible, it is possible, then that's things. But avalanche cannot able to reach this voltage, cannot able to experimentally reach this voltage. By hypothetically, by imaginatively, he can explain, he explained that yes, after a certain time a huge current flow, but to reach this voltage, whenever we are just doing this experiment, the 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 diode was burned. Why? Because a huge heat is evaporated, a huge heat is developed, and for that reasons the diode is burned. So this is how we can reduce this voltage. This things is next matter. We'll come for these particular things also. Basically in the forward bias, In case of forward bias, we can represent it as a switch. Diode is representing as a switch, and is the reverse bias, we are representing it as a switch on. This is the on conditions, this is the on conditions, and in the reverse bias we can say diode it as a off conditions, on conditions and the off conditions. Okay, so in case of the diode, there is a as the PN junctions is there a depletion region, so very small amount of voltage V is there, very small amount of voltage V is there, and this voltage is specifically, this voltage is representing like that way 0.7, and this is the 0.7, the practical diode, and this is the practical diode in the reverse bias. Okay, practical diode is the forward bias, practical diode is the reverse bias condition, that is representing by this picture and this picture also. Okay, so diode is actually representing here as a switch, diode is actually representing here as a switch. Okay, now now come to the matters about these junctions. Uh, this is the structure of silicon. We know about these things. No, we know about all these things. But things is that in case of reverse bias, what will happen? I want to understand about that. So suppose it is the PN junctions, and suppose it is the P-type material. So if it is P-type material, so what happened? I am just uh, doping by aluminum. We are just doping by aluminum, and by the aluminum, if I am doping here some some A some A, there is some aluminum is there, and some hole is generated. For the purpose of the aluminum, some hole is generated. So because I am doping by two aluminum atoms, suppose I am just doping by two aluminum atom, two aluminum atom, two aluminum al, two aluminum. By this two aluminum I am just doping. Okay, only two. Okay, now next, suppose this is also intrinsic semiconductor, I want to make it extrinsic. How it can be possible? I am just doping it by the pentavalent. Pentavalent means suppose phosphorus is the pentavalent. Suppose phosphorus is the pentavalent, and as the phosphorus is the pentavalent, I am just doping by the phosphorus, that is P, and that is also P. So if when it is pentavalent, I am just doped by the pentavalent, so one electron is generated, another electron is generated. Here one electron generated, and in the previous case two holes, that is occupied occupied hole is generated. This is hole actually. This is hole. For the aluminum, two holes are generated. Okay. So in that case, there is a there is a electron generated. So this is the N type, and you see in the previous type, this is the P type material. This is a P type material, and this is the N type material. Okay. Now, what happened? Oh, sorry. Yes. So, what I'm saying, that is, so this is aluminum, and this is aluminum. So for that reasons, one hole is generated, another hole is generated. So this is P type material, and the next case, this is phosphorus, and suppose this is phosphorus, and one electron and another electron is generated. Two electrons are generated. Okay, so this is become as a N type, this is become as a N type, and this is become as a P type. P type, and this is become as a N type. P type and N type. Okay. So as this is the P type and N type, so what happened? Uh, so this is the P type and N type. So now what happened? This is the moderately doped. You show there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 numbers of silicons is there, and 2 phosphorus only doped. Okay, here also same things is happened. 12 number of silicons is there, and then only 2 numbers of aluminum is doping by 2 numbers of aluminum in here. One is this, one is this. Okay, 2 numbers of aluminum only doped. Okay, so uh, now uh, what is our target? Our target is that I have to reach this particular voltage. I want to reach this particular voltage. In the reverse bias, I want to reach this particular voltage. How we can reach this particular voltage? That things is necessary. Because I have to reach this particular voltage, the diode will not burn. This is our actual target. Engineering target is that in the reverse bias, I am giving the voltage in here. I am increase this voltage, but we want to reach this particular voltage, but diode will not burn. But to reach this voltage, it is mandatory that we have to make something change in these PN junctions by which it can be possible to reach this voltage. Suppose I want to explain one very important thing. Suppose there is one wall. Will show one wall, and wall is created by some bricks. This is the wall, and this wall is created by some bricks. To show some bricks is there, and in these bricks all the cements are there. These are the cement which can able to join all these bricks. All these bricks are joined by the cement. Suppose this is one bricks, this is one bricks, these two bricks are joining by the cement. Okay, and if these two bricks are joined for the cement, so if the cement is too much impurated by the sand, if the cement is too much impurated by the sand, then what happened? If the cement is too much impurated by the sand, then what happened? Then happened is that then this uh, this wall can be easily break. Then this wall can be easily break. Is not it? Suppose you have one wall, and if this wall is all the bricks are connected by the by some cement. Okay, if the if we can increase the sand in the cement, then automatically wall is broken, because it is highly impurated. So one thing I want to know, that what is our target actually to reach this particular voltage. We have to break all these bond. We have to break all these bond. So how we can break this bond? We have to make high impurity. We can introduce high impurity in this. Then it can only possible to break this bond. Then it can possible to break this bond. So how we can introduce high impurity in this particular bond? How we can introduce the highly impurity in this bond, in this thing? For that reasons, we have to make it highly doped. We can increase the doping high. If I'm increase the doping high, then automatically bond can be break easily. Automatically the bond can break easily. So what happened? We just highly drop it. Aluminium. So 1, 2, 3, 4 and 5, that is aluminum. So you show 1, 2, 1, 2, 3, 4, 5. 5 numbers of holes automatically create, and here also I am highly doped these things, that is highly doped. We can highly dope 1 2 3 4 5, that is also create highly 1 2, that is also create high electron concentrations in here. So it is high doping concentrations is high, doping is high. In case of that, doping is high. So when we can introducing the highly dope, when we can introducing the doping high, then it can be very easily to reach this particular voltage, because at that time the bonding capability, it is actually the voltage is required to break the bond. So the bonding strength of all the silicon atom, bonding strength of the all semiconductor atom as it is highly doped is become low. So for that reasons, very easily we can able to break the bond. So for that point of view, it is called so for that point of view, we can very easily uh, break the bond. And for that reasons, if we can introducing the highly doped p-n junctions, it is just a highly doped p-n junctions. If I increase the doping, then it will convert, it will convert from a p-n junctions to a diode, that is called Zener diode. We just convert a p-n junctions to Zener diode. We highly doping. If I'm increase the doping, then automatically it's change. If I'm increase the dope, then automatically it's change. Then it's become a highly doped p-n junctions, and highly doped p-n junctions nothing but a Zener diode. So there is a difference between the avalanche breakdown and Zener breakdown. What Avalanche said that the bond is breaking, that things that hypothetically, and Zener can able to reach this particular voltage through becoming highly doped, to doing this experiment highly doped diode, and just make this highly doped diode. So for that reasons, that diode is developed which can able to reach this particular voltage. And for that point of view, as Zener can able to reach this voltage, that is called the Zener breakdown voltage. So in that case, that is called the reverse breakdown, and in this reverse breakdown, that is called the Zener breakdown voltage. And highly doped diode is called the Zener diode. Highly doped diode is called the Zener diode. So thank you very much for this purpose. Actually today I am not completing about able to completing all these things. I will again continue these things, Zener diode and some difference between Zener diode and its applications, all these things for the next video. Thank you very much. Thank you for watching.